Well, hello and welcome to our 36th session. In today's session, we're going to start our new topic, the metal oxide semiconductor field effect transistor, affectionately known as the Mesfet. And we're going to start off with kind of a generic field effect transistor, specifically the deposited channel field effect transistor. The Mesfet is a device, is a transistor where the channel, the conductive channel, is formed by inversion. But there's another type of semiconductor device, specifically a field effect transistor, where the channel is deposited. So we're going to talk about the deposited channel first and how the gate controls the conductivity of the channel. And then we'll get into the Mesfet current voltage characteristics. But first, we're going to start off with a wonderful performance by the marvelous violinist Hilary Hahn, the finale to Mendelssohn's Violin Concerto, and we'll see you here in about a little over 5 minutes. This is a kind of rough outline of some of the topics we'll be covering today. The first topic we're going to be looking at is something I'd like to call, for want of a better term, a generic field effect transistor. And then we'll be looking at that generic field effect transistor with respect to its IV or current voltage characteristics. We'll be doing that in a qualitative way with relatively little mathematics. And then we'll be breaking that down further, and we'll be looking at one specific type of field effect transistor, and that is the deposited channel field effect transistor. And then we'll be breaking that down further, and specifically we'll be looking at something called a Mesfet. And then we'll be examining the Mesfet in a little bit more detail before we go on to the MOSFET. And the difference between the Mesfet and the MOSFET is, well, it's a change of one letter. MOSFET is the metal oxide semiconductor field effect transistor. The Mesfet is the ME, the metal, ME, metal semiconductor FET. And we'll probably, hopefully, by the end of the session, we'll be somewhere in this region, and we'll maybe able to at least introduce the MOSFET. And then we'll end, I should mention, with a wonderful aria from Giuseppe Verdi's La Traviata, Sempre Libre, Forever Free. Okay, so when we talk about field effect transistor, we're talking about field. What kind of field? Electrical field. And once we mention the term electrical field, we really need to remember that really what we're talking about is voltage. Voltage and electric fields are kissing cousins. So we'll be using an electric field, unlike the BJT, we'll be using an electric field at the input to control an output current. In the BJT, we used an input current, namely the base to emitter current, to control an output current, namely the emitter to collector current. And the term generic seems to say that there are more, or there may be more than one type of field effect transistors, and that indeed is the case. However, in all of them, they have the same characteristics. They use electric fields at the input to control output currents, and because of that, we'll be talking about something. Actually, you'll be learning more about this when you study something called, study electronics. They talk about, in field effect transistors, the transconductance, and that's the ratio of output current to input voltage. Now, if you take this term apart, conductance is just the inverse of resistivity. And go back to Ohm's law, the resistance is equal to voltage divided by the current. The conductance is equal to the current divided by the voltage. Just flip it on its side. And the transconductance means, or implies, that the current that we're talking about is not the output, is the output current. It's the IDS, or the drain, or the source to drain current, and the voltage is the input voltage. Specifically, it'll be the gate voltage. So that's why the trans comes in, because one side of the equation, the numerator is the output and the denominator is the input. So there is literally a transconductance. And we like a small input voltage, specifically on the bottom of the numerator, to control a large output current. So we want high transconductance. And also, just as important, we want the output current to depend only on the input voltage. And that's exactly what we saw in the BJT in operating in the forward active mode. And the other thing is we'd like ease of fabrication, we'd like high reliability, small size, and a bunch of other things which make the devices useful, which we won't be talking about in these sessions. So let's get started with a deposited channel field effect transistor. So what we're doing here is we have a semi-insulating. This is probably going to be gallium arsenide, and we're going to deposit a conductive layer on top of the gallium arsenide wafer. And then on top of the conductive layer, we're going to deposit another conductive layer. Now, the first thing you're thinking of, that's a really silly idea. Why don't we deposit one conductor on top of another conductor? Well, this conductor here shown in green is a very special kind of conductor. It is a crystal conductive channel. And just to give you an idea, semi-insulating gallium arsenide wafer maybe runs in the range of $100, $200. A gallium arsenide 6-inch wafer, which has a N-type conductive channel deposited on top of it, can run probably well over $1,000. So most of the cost is in the deposition of this conductive layer, and this is done by a process called epitaxy. Epi means like or same, taxi layer. So the idea is we put a semiconductor layer on top of a semiconductor, and if we put now a gate metal on top of a N-type semiconductor, we have a Schottky barrier. Well, no, not yet. We have to make sure that the gate metal is conducive or compatible with a rectifying Schottky barrier. And if we're talking about gallium arsenide, gold is a pretty good choice. So gold on top of a N-type conductive channel will give us a Schottky barrier, which means that we now have a depletion region underneath of the gate. The thickness of the conductive layer we're going to call T, but the conductive channel we call A will be less than T, because part of that conductive layer is made up of a depletion region where there are no charges. So A will always be less than T. And these few sentences basically go over what we just said, that if we deposit a N-type channel conductive layer which is crystalline, and we use a gold on top of that, we get a Schottky barrier, and we get a depletion region. And now controlling the width of the depletion region by controlling the voltage on the gate will allow us to reduce this or increase the size of the conductive channel, controlling the resistivity and making a field effect transistor. Now, if we look at again going back to a very generic case, where we have some conductive channel of thickness A, and we're eventually going to put a voltage between the source and the drain, here, source and the drain, and if I was able to reduce my size to submicron and have a little submicron voltmeter, and I basically measured the voltage across the channel, it would go from 0 volts at the source to the voltage VDS at the drain. And that's very important, because there's going to be a voltage along the channel which is going to vary linearly from the source to the drain. So now we can go back and look at the resistivity, and the resistivity is equal to, this goes way, way back to our first sessions, it's just 1 divided by the conductivity. And the conductivity is given by NQ. NQ is coulombs per cubic centimeter, multiplied by the mobility. And that is our basic equation, and that's the one we're going to be looking at in some more detail. First, let's check the units. Okay, so the units of this thing here, the denominator, are NQ is coulombs per cubic centimeter, and now we want the units of mobility, and we've shown a number of times previously, specifically in Chapter 7, that the units of mobility are centimeters squared per volt second. So therefore, the units of resistivity for the, not the conductivity, but the resistivity, we just flip it and we get volts centimeter. Notice for the conductivity, volts centimeter is in the denominator. In resistivity, it's in the numerator, divided by coulombs and multiplied by centimeters. Well, now let's see if that makes sense with regard to Ohm's law. We know the units of resistivity for Ohm's law are just ohms, and 1 ohm is a volt per amp, or in our case, milliamps. Okay, the units of volts are, well, volts. What else? So the units of volts are volts. The units of amps are coulombs per second. So the units of resistivity are volt seconds per coulomb. And then if we compare that, I should say, did I say resistivity? Volt, the units of resistance are volt seconds per coulombs. The units of resistivity are volt seconds per coulombs multiplied by centimeters. So therefore, it is pretty obvious that the units of resistance are the units of resistivity when we take out the centimeters. The resistivity has the units of ohm centimeters. This part is ohm multiplied by centimeter. Now we can go a little bit further and we get the relationship between the resistance and the resistivity. Those are different. And the resistance, using Ohm's law, is just given by the resistivity multiplied by the length divided by the cross-sectional area. Notice that I used the cross-sectional area of the conductive channel, not the area, or not the thickness of the deposited layer. And this is the thing we're going to be controlling. And this makes sense because the bigger, the longer the L, the longer the resistance, and the bigger the cross-sectional area, the smaller the resistance. And this has the units of, all this part L over WA as units of 1 over centimeter, and multiply that by units of resistivity, which are ohm centimeter, I get ohms exactly as I would have expected. And now we can just use Ohm's law. Current is equal to voltage by resistance. Substitute for the resistance from equation 20.2, and we get equation 20.3. And this is our basic equation. We're going to vary the VDS. We're also going to find a way to vary the A, and both of those will give us IDS, the source to drain current, or I should possibly say the drain to source current, the current that exists along the channel. And the whole idea is to make IDS dependent only on the variation A, and to take away the control of VDS. And that's what we're going to be spending some time doing. But before we get to that, just looking at this equation as it sits, for a constant A, this is just a linear equation of slope WA divided by rho L. As A increases, the slope increases. And that's what we show here. If we have an increasing A, A1, A2, A2 is greater than A1. Therefore, we would expect that the slope of this curve here would be greater than the slope with the smaller cross-sectional area. So if we look a little bit more closely at two generic structures, one will be the deposited channel, and that's what we've been talking about up till now. The channel must be doped, and it must be crystalline, so I probably should have added that here. We're going to control the magnitude of the source to drain current by controlling the channel width, which we refer to as A, and we're going to use the symbol W without a subscript, somewhere back here, to denote the width of the channel into the paper. But if we put a subscript on the W. That will be used to denote the dimension of the depletion width. So W with a subscript plus A will be equal to T. And we're going to be talking about that a little bit later on. Okay, let's look at now 3 types of deposited channel generic field effect transistors. On the left side, we have the JFET or junction FET, and here we have PN junctions. We have basically semiconductor. We have in a PN junction always, we always have depletion regions at the 2 sides. So we control the gate voltage. We can either squeeze the channel or open the channel by putting a forward or reverse bias on the gates. Forward bias, we open the channel. Reverse bias, we squeeze the channel shut. This is the one, the gallium arsenide Mesfet, which we've been talking about and will continue to talk about a little bit a few minutes. And this one is kind of a hybrid between the JFET and the gallium arsenide Mesfet, and this is called a SIT or SIT, static induction transistor. We won't be saying anything about this. We'll be saying a little bit about it in the last chapter, the last part of the last chapter 24. But just a few words about it here. This is a hybrid because we have a Schottky on the gate, just like we have on the Mesfet, but we have a vertical structure in the SIT, just like we have in the JFET. So this is generally, we'll use something called silicon carbide, which has an extremely high melting temperature of probably, I think, 16 or 1700 degrees Celsius, whereas gallium arsenide, the melting temperature, I believe, is in the range of 600. So this is about 1,000 degrees tougher than gallium arsenide. It also uses, just like the JFET, it's a vertical device, and it uses a source contact on top of the device and a drain contact, which is generally the substrate itself. Here, I have to apply a Schottky. Generally, this is done at somewhere about 500 or 600 degrees Celsius, but the source contact must be applied at a much higher temperature and then alloyed in, because Schottkys and ohmics are very, very different, and that's one of the difficulties in actually fabricating a SIT, because we have 2 types of metal semiconductor junctions. One, a Schottky, which is rectifying. We sure don't want a rectifying junction here. We want an ohmic junction, so we have to deposit the source metal, which is a different metal. This metal, I believe, is nickel, and this metal is gold. So we have to deposit it at a higher temperature, and then we have to alloy it with the semiconductor, and that is done at extremely high temperatures. That's a trade secret by it, and I don't remember it anyway. I used to do it, but I don't remember. I think it's on the range of 12 to 1300 degrees centigrade. Okay, so this paragraph, basically, I describe exactly what this figure depicts, so we've already discussed that. Okay, so maybe just the last sentence. If a condition could be created in which only the gate voltage controls the output current. Here, gate voltage controls the source to drain. Gate voltage controls the source to drain in this lateral planar structure. And here, the gate voltage controls the source to drain current in this vertical. And that is our goal, to discover conditions in which that can be achieved. Now, the second type of generic FET, which we'll be spending much of our time discussing, is the MOSFET, and the MOSFET has no deposited channel. It is an MOS structure, MOS, and we invert the silicon at the surface to basically artificially produce a conductive layer right below the oxide. Now, whereas this conductive or this channel may be 2 to 3 or 4,000 angstroms, the thickness of the inversion layer is going to be so small that it is unmeasurable, at most a few tens of angstroms. So that's one difference between the MOS structure and the Mesfet structure. Okay, so let's just take a minute or two to talk about one specific type of deposited channel field effect transistor, the JFET. We won't be discussing this in any detail, but it's a good place to start. So if we take this guy and we rotate it, which is what we've done here, and then we cut it off, we only look at part of it here. So we're only looking at this gate, this semiconductor, P plus, silicon, and the channel region. So again, we have the deposited, or in this case, grown N-type silicon, and then we have a depletion region, because we always have a depletion region in a p-n junction. So we're going to have a depletion region width, which we call W0, with no gate voltage, and therefore the channel from source to drain is going to be less than T, and A plus W0, of course, is equal to T. W0 is given by this expression, which we've seen in the p-n junction, we've seen in the Schottky, we've seen in the MOS, all over the place, like you know what. The only difference is the different barrier types. So we're going to call that a generic VB, V for voltage, B for barrier, and let's just take a look at some relatively simple rules for writing this without going through a rather big struggle in deriving it, God forbid, or in looking it up even. We can write it simply by just writing it down. And the first rule is that W is proportional to the square root, and the reason is there are two integrations from Poisson's equation. The first, we're starting from the fixed charge concentration rho. We integrate once to get electric field. We integrate twice to get the voltage. Each of those integrations involves a power, so the field is linear, the voltage is parabolic, and when we isolate the depletion region, we have to have the square root, because if we had an expression for the voltage in terms of the depletion region width, we would have a parabolic, a square. So that's where the 1/2 comes from. Q and N, in this case it's donor doped, are always coupled together because this is coulombs per cubic centimeter, and if we separated those, we'd be in a nonsensical situation. So Q and doping density are always multiplied together. We'd like to have those on the bottom because the ND, the units of ND, are centimeters to the -3, so we bring up a centimeters to the +3 on top, which is close to what we want. So we're figuring we probably have something divided by centimeters to get that to be centimeters squared. The units of voltage are, well, again, they're volts. it could be easier than that. So the only thing we have to worry about are the units of permittivity. Well, we can do this now by sight. Permittivity has to be on top. Why? Because this is a number on the range of 10 to the minus 2, 10 to the minus 3. W0 is extremely small, so we want something really small. The only thing that's small that is a material parameter, electrical material parameter, is the permittivity. So we're not hard-pressed to put the permittivity in the numerator, and the only problem is getting the units of permittivity just as a check. Well, it has to have volts on the bottom, and it has to have centimeters also on the bottom, and it has to have coulombs on top. So the units for permittivity are coulomb per volt centimeter, which makes everything turn out precisely right and makes it really easy to write the depletion region width by inspection without having to look it up. And of course, equation 20.6, pretty straightforward. The actual part of the channel which will be conductive is equal to the channel of the deposited thickness T minus W0. This is in equilibrium because this is a depletion region width at equilibrium. And that is basically shown right here. So A is equal to T minus W0. Putting in some numbers for a P plus N doped semiconductor, the P plus gives us about half of the band gap for silicon, 0.55, plus the extra part due to the doping. And if we're doping at 10 to the 16th, a little bit on the low side, we'll get a difference of 0.3. This is actually incorrect. Let me correct this. This should be 10 to the 15th. Let me just put that in here. This is a 5. 10 to the 15th gives an extra 0.3. So 0.3 plus 0.55, 0.85. Put all that in and we get about 0.33 microns. And that's a pretty good number for the depletion width. And let's see, what else do we have here? Of course, if we had a T of, say, 0.5 microns, then the A would be 0.5 minus 0.33, and we can see that the channel, the conductive channel, has shrunk quite a bit, even at equilibrium. And it is possible that the entire channel could be basically cut off or depleted. It is possible that W0 will be equal to A. That's quite possible if two things. Either one, the doping on the N doping is less, very lightly doped, or we put a bias on the gate. And specifically, we put a bias on the gate which drives electrons away, increases the W0, in other words, a reverse bias, and in that case, we can actually make the depletion width equal to the T, and cutting off the channel completely. And don't think that's a bad thing. That's actually a pretty good thing. We say the entire channel is pinched off, because you think of pinching something, you're basically closing it up. Alternatively, we're going to use pinch off in a little bit different way, but here, that's why I emphasize the fact that the entire channel is pinched off. Alternatively, and this is the term we'll be using, it is cut off. There ain't no conductive channel. And no matter how high the drain to source voltage, we get no current because there is no channel. And I guess the reason that it was reasonable to do the JFET first, because it leads us right into the Mesfet. The Mesfet is the same thing, except instead of having a PN junction, we have a Schottky barrier. So we have one type of semiconductor. This would be gallium arsenide semi-insulating, and then we have a N-type doped deposited region of thickness T. We have a depletion region under the gate of width W0, where now VBI is due to the fact that we have a Schottky barrier here, and it depends on the difference between the metal semiconductor work function and the metal work function and the semiconductor work function. So VBI is something that we have studied quite a bit in chapter 8, 9, and 10. And as we mentioned previously, it is very important to choose our metal type. In this case, we choose gold or gallium arsenide, such that we get a Schottky barrier. In a JFET, we always have a barrier. In a Schottky barrier, well, we only have a barrier if there is, well, a barrier. And that depends on the difference between the work functions between the gate metal and the semiconductor. And if we don't have that, if we made a boo-boo and we have an ohmic junction, then there is no way to control the channel width, and we always get a full open channel, and that is not a good thing at all. Okay, so let's assume we're starting with a Schottky barrier. I emphasize it's a barrier, so there is a depletion region. So we have some depletion region width, W0. The 0 denotes that it's in equilibrium. And now we're going to apply a gate voltage. So if we apply a voltage onto the gate in a Mesfet, we can either widen the depletion region if it's reverse bias, or we can narrow the depletion region if it's in forward bias. And let's take a look at what we're saying here. Here VG, this is the gate. I'm going to apply it not equal to 0. So I've denoted the depletion region width as WG, where the G stands for gate. It can either be bigger, reverse bias, or smaller in forward bias. However, and this is the takeaway from this figure, it doesn't matter. If I look at the energy band diagrams, it doesn't matter if I cut it over here or over here, because the entire length has the same depletion region width. This line here, which denotes the demarcation between the depletion width and the conductive channel, is horizontal. So if I take a look at the energy band diagram, the bands bend up. They always bend up for N-type semiconductor at the interface between the metal and the semiconductor, starting at equilibrium, which is shown in red. Forward bias, the bands bend less, depletion region shrinks. Reverse bias, the bands bend more, and the depletion region widens. This is for VG positive, and for VG negative, we have reverse bias. And the easy way to remember that is, for negative bias on the gate, I am pushing away mobile electrons, leaving the positive fixed ions in the depletion region. Okay, so just to summarize, it doesn't matter at what point Y we take the cut, these curves will be exactly the same. Now let's take a look at this one more picture, and here we have it. It's kind of a crowded picture here, but no source to drain voltage. However, we look at three different gate biases: one 0, where we have W0, one forward bias, where we have W1, the depletion region is pushed up, and one reverse bias, where we have a gate bias which is negative and the depletion region widens. Each one of those has its own unique conductive channel. So we can summarize this as one equation, equation 20.8, that the depletion region with W, and here I've denoted it in general by the subscript G, which tells me that it depends on the gate voltage. Gate voltage negative, then the depletion region widens. Gate voltage positive, the depletion region shrinks. This is not that clear with the plus minus. However, here it is, at least for N-type semiconductors, explicit. If VG is negative, then this term becomes positive, and WG is bigger. If VG is positive, then the depletion region shrinks. So you can see it explicitly. And this little equation here, which we've seen umpteen times, just basically repeats that. The conductive part of the channel is equal to the positive part of the channel minus the depletion region, which is a function of the gate voltage. That's all that says. Now, let's see. We're going to put a gate voltage that is sufficiently negative so that the conductive channel completely disappears. All right, and therefore, what we're saying in this particular case, that the depletion region is equal to the complete deposited channel thickness. And let's just put that in. Let's find out what that particular voltage is, what VBI minus VG is for that particular case. So instead of A, we put in T. It has to be squared. And of course, now we have to choose an ND. Well, let's choose 10 to the 17th, which is a pretty good number. Putting in all the numbers, we find that this rather strange voltage, we'll talk a little bit more about this in chapter 24, but we're going to kind of leave it for here, not talk too much about it. Works out that it is plus 3.2 volts. Now, this is not the gate voltage. We can find the gate voltage by simply using this simple equation here, right over here, and we find the gate voltage in this particular case is minus 2.4 volts, and that's a pretty reasonable number. Okay, and that also assumes, by the way, that the equilibrium barrier, I should have mentioned that, is about 0.8 volts. Not bad for Schottky, anywhere from 0.7 to 0.8 volts. If it was a PN junction or a JFET, instead of 0.8, this would probably be closer to 1 volt. Okay, now we're at the last part of our qualitative discussion, and that is we're going to add a drain to source voltage along the channel. So going way back here, now we're going to allow VDS to become greater than 0. We're always going to make the drain positive, in this particular case, source with ground, and let's see what happens there. So now the channel voltage, which started out with way back when, is now positive. And if we have a positive voltage on the channel, it's like adding a negative voltage to the gate. So what happens is the depletion region widens, but here's the important point. The widening is now a function of Y. So this direction from left to right, I probably should have put an arrow here. This is the Y direction. So now the widening is a function of the position along the channel. And that is represented here in this diagram. The conductive part of the channel shrinks along Y. The depletion part of the channel is now a function of Y, and it increases. So here the Y is shown explicitly. So that's with VDS greater than 0, and that is really a big deal. So now, if I want to draw the energy band diagram, it depends on where I cut. If I cut here, I've got a relatively large conductive channel and a small depletion region. If I cut way back over here, shown in this part, I've got a very narrow conductive channel and I have a large depletion region width, and that is shown here. If I cut at the source, y equals 0, I have a little bit of band bending. If I cut at the drain, I have lots of band bending, and the difference is the source to drain voltage, VDS. And I wrote this in somewhat larger font because the key takeaway from all of this, when I apply a source to drain voltage, the field effect transistor does no longer have a horizontal depletion width demarcation. It has a depletion width demarcation, this dotted line, which changes as a function of y. Now, one of the important things which we should mention here, that in the x direction, this direction here, we have material equilibrium. There's no flow. Remember that material equilibrium or material disequilibrium depends on whether there is a flow of material. There's no flow here because we have this big non-conductive region. However, there is flow from the source to the drain. So I have a situation where I have non-equilibrium in the y direction and I have equilibrium in the x direction. And just one more way of looking at this non-equilibrium in the y direction. Here, of course, is the energy band diagram, so I have x as the horizontal, but in the cutaway, I have y as the horizontal because this is a sort of a schematic of what's going on. So if I look in the y direction, here, it's exactly like I have a conductive material with two connections, source, drain, and applied voltage between them. What happens, because I have non-equilibrium, the Fermi level slants down. It is more in the positive side. It is lower than on the grounded side, and all the bands, the conduction band and the valence band and the intrinsic band, all bend down. So what we're saying here is that the Fermi level is lower on the drain side than on the source side, which means that I have more band bending on the drain side than the source side, because the Fermi level is further below the intrinsic on, or I should say on the conduction band edge on the drain side than it is on the source side. So that's why we have more band bending at the drain side or drain end than we have at the source end. So that's just a different way of looking at the, this concept. Okay, the energy band diagrams are pushed down as we increase in y from 0 to L, in other words, from source to drain. Okay. Now if we go back to our original, way back when, Ohm's law formula, substitute in for R, and that's what I've done here. And we have the, just basically the same equation that we had a number of pages ago. Depletion region and the deposited channel minus the depletion region. This is my A. It's now a function of Y. I substitute for rho, and as long as VDS, however, is not too big, and I haven't pinched off the channel. I haven't closed the channel. Okay, so we still have a nice IDS, but it's not quite linear now, because now the slope, if this was a resistance was constant, then this would simply be a straight line. But now the resistance is not constant as a function of y. So this is not really quite as simple and pleasant. Well, actually, it's more pleasant because this is the way the device works, but it's not as simple as we had previously. Let's take a look at this in figure 20.13. We have a constant VDS. We have two gate voltages, one which is either more positive or not very negative, and that shows a wider conductive channel. And now we make VG2 more negative than VG1. The curve shifts. Now notice, however, that the slope of these lines is the same, because V channel, as we move along the channel becomes more and more positive, which is the same as making the gate more and more, I should say, here's the channel here. Sorry, I move from the source to the drain along the conductive channel, and the channel becomes more positive. It's the same as making the gate more negative, and therefore the channel tends to be closed off. So if you look at the IV characteristics, especially this curve right here, VG2, we find as we increase the source to drain voltage, the curve tends to flatten out. And that's exactly what we're seeing here. So now if we increase the VDS, keep making it bigger and bigger and bigger, we get to a point where the channel can be completely closed off at the drain, only at the drain. So this point down here with a increasing VDS, this slope for a given gate voltage, the slope would increase. I probably should draw that in. For example, suppose we have a VG2, but VDS now is increased. This point would stay the same, but the point here would shift down until we have a curve which has a higher negative slope. And right at this point at the drain, it could be, if it's high enough, it could be completely closed off, or we say it is pinched off. That special value of VDS we call VD sat, or VD saturation. And any value above VDS, or above VD sat, I should say, will divide the channel into two parts: a high resistivity part. For example, suppose this is closed off, so I have a high resistivity part in here, and I have a channel part during the rest. All voltages above VDS will be dropped across the high resistance part of the deposited channel, and that is something we'll have a little review of that next time. And if I put that into our basic drift equation current, I get a J sat, or a current density sat, which is NQ. This is velocity. Velocity is equal to mu times the electric field. Electric field is voltage divided by L, and that's where I get equation 214. And what we're saying here is that we have a high resistance area of the channel right around the drain region, and that region is pinched off. And that is what is shown here. This is the pinch off point, and our VDS has now gotten to the point where from this point here to the end of the gate, which is denoted by little l, this is a high resistance region, And the voltage drop across here is such that the electric field is very large in this region, just like, in fact, precisely like the base collector junction in a BGT, which is reverse bias. I have a large electric field. So the voltage across the channel region, here, this is the channel, this is the pinch-off. The voltage across the channel stays constant because all the additional voltage above VDSat is dropped across the high resistance region. So that the current now, the IDSat, which corresponds to VDSat, no longer depends. I should say this really slow and really loud, but I won't do that because I'm a nice guy, calm. Anyway, the IDSat is now a function only of the gate voltage. And finally, we have a useful device, and here we see that depicted here. Above VDSat, the IDSat flattens out, and the IDSat in this region here only depends on the gate voltage. So we will stop here. We'll just very briefly review this next time, and we will start at this point, and then we will summarize the Mesfet, and we will end with a marvelous clip from Traviata. Alfredo has declared his love for Violetta. Violetta wants no part of it. She likes to exist for parties and pleasure, and she sings the song Sempre Libera, forever free, and we see we see it in the movie, but the idea is that in Violetta's conscience now she's torn between being free and her love for Alfredo, and Alfredo appears in her mind, and he says, love is the heartbeat of the universe, gratia delicia, which is a marvelous phrase, delicious torment. So let's listen to enjoy Sempre Libera from Traviata, and we'll see you next time.
Joy! Joy! Sempre figlio e tu